Norway is undertaking a project that seems almost impossible, building a highway over 1,100 kilometers long, crossing fjords more than 1,000 meters deep, over 3 times the height of the Eiffel Tower. No foundations, no supporting pillars, only ultra-long suspension bridges, subsea tunnels, and even floating tunnels suspended beneath the water. This is the ferry-free E39, a mega project worth over $40 billion, aimed at completely eliminating coastal ferries that have constrained Norway's economy for centuries. How do you build a bridge when the seabed lies far beyond the reach of any foundation? And how can humans keep a tunnel stably suspended within constantly moving water? That is the journey we're about to explore right now. To understand why Norway is willing to spend tens of billions of dollars on a single highway, we first need to look at the country's harsh geographical reality. Norway's western coastline, where the E39 runs, is one of the most complex terrains on Earth. It is not a straight line, but a vast labyrinth formed by more than 1,190 fjords. Towering cliffs rise thousands of meters before plunging straight into the deep ocean below, creating breathtaking natural beauty, but a true nightmare for transportation infrastructure. For centuries, this region has been completely fragmented. Today, traveling the full 1,100 kilometers from Kristiansand to Trondheim can take up to 21 hours by car. And most of that time isn't spent driving, it's spent waiting for ferries. That's why Norway has no other choice. They need a radical solution to stitch together their western corridor. The E39 coastal highway route was conceived to eliminate ferries entirely, cutting travel time from 21 hours down to just 11, and more importantly, creating a unified labor market for over 1/3 of the country's population. The project officially broke ground in late 2017 with the Rogfast subsea tunnel, which has now entered its peak construction phase in 2026. While some of the deepest tunnels in the world are gradually taking shape beneath the ocean floor, designs for crossing the Sulafjorden are still undergoing final technical refinements, promising a leap forward in materials science and marine dynamics, unlike anything the world has ever seen. However, to turn this ocean-spanning vision into reality, engineers must confront a formidable natural fortress, Norway's fjords. These oceanic chasms are unimaginably deep. For example, the Sognefjord plunges to more than 1,300 meters. If you were to place the world's tallest building, the Burj Khalifa, on the seabed, its tip would still lie nearly 500 meters below the surface. At such depths, constructing traditional concrete bridge foundations becomes virtually impossible due to immense water pressure and the enormous cost of stabilizing the seabed. Beyond their depth, these fjords can span 4 to 5 kilometers in width, flanked by sheer granite cliffs on both sides, pushing conventional suspension bridge designs beyond the physical limits of steel cables. On top of that, the harsh North Atlantic climate, with violent snowstorms and powerful ocean currents, means any structure here must withstand forces far beyond standard engineering conditions. When traditional bridge-building methods reach their limits against fjords over 1,000 meters deep, Norwegian engineers were forced into a revolution in engineering thinking. Instead of trying to anchor massive concrete pillars to the seabed, they drew inspiration from offshore oil and gas technology, transforming giant oil platforms into floating foundations for bridge towers. At the arena of the 3.7-kilometer-wide Sognefjord, they are not just building a bridge, they are setting new records. Bridge towers rising 150 meters taller than the Eiffel Tower, and suspension spans stretching to nearly twice the length of current world records. In fjords that are extremely wide, yet incredibly deep, suspension bridges become the preferred solution. However, to cross the Sulafjorden, engineers are designing a suspension bridge with a main span of up to 3,700 meters, twice the length of the Golden Gate Bridge in the United States. In such vast and deep fjords, ultra-long-span suspension bridges are the most viable option, as it is impossible to place supporting piers in the middle. First, engineers construct two massive concrete towers on land or nearby islands, each rising to around 400 meters. Then the main cables made of high-strength steel are stretched between the towers using the air spinning method, where tens of thousands of thin steel wires are spun back and forth and bundled into enormous cables. Once the main cables are anchored into large concrete blocks at both ends of the bridge, vertical suspender cables are installed to hold the steel deck segments. These deck sections are transported by ship and lifted into place piece by piece until they form a continuous bridge stretching several kilometers. Finally, the structure is equipped with aerodynamic design features and damping systems to withstand vibrations caused by strong winds from the North Atlantic. For fjords that are both too deep and too wide for traditional suspension bridges, Norway has introduced a bold solution. Borrowing technology from deep-sea oil and gas platforms. Instead of building fixed pillars anchored to the seabed, something virtually impossible at depths exceeding 1,000 meters, the entire massive steel roadway is placed on floating pontoons made of high-strength reinforced concrete. Each of these pontoons is roughly the size of a football field, with buoyancy precisely calculated to support tens of thousands of tons of bridge deck above, while maintaining absolute stability against tides and ocean currents. To prevent the bridge from drifting in the harsh northern seas, engineers deploy a complex multi-point mooring system. These mooring lines are bundles of high-strength steel, with diameters exceeding 20 centimeters, connecting the floating pontoons to gravity anchors weighing thousands of tons, embedded deep into the seabed rock. The system is designed to withstand winds of up to 160 kilometers per hour and waves over 15 meters high. This represents a perfect fusion of naval engineering and civil construction, where AI-driven sensors continuously monitor and adjust the tension of the mooring lines in real time with millimeter-level precision. The result is a dynamic architectural marvel, capable of standing firm in places once considered the absolute limits of human engineering. At specific locations such as the Bjornafjorden, before any construction begins, engineers must thoroughly survey the entire fjord, including seabed topography, water depth, currents, wind, and wave conditions. Based on these findings, they have proposed a bold hybrid solution, a suspension bridge supported by floating towers. Instead of fixed concrete foundations, massive bridge towers will stand on floating pontoons suspended in the water. These pontoons are stabilized by enormous concrete structures, typically 60 to 100 meters long and dozens of meters wide, anchored to the seabed with steel cables to maintain their position. The floating units are constructed in coastal shipyards, with multiple hollow chambers inside to provide buoyancy. Once completed, they are towed to the construction site and secured using mooring systems or heavy anchors embedded deep into the seabed, ensuring stability against waves and wind. On top of these large floating platforms, engineers erect the bridge towers and stretch the main suspension cables, similar to a traditional suspension bridge. Finally, steel deck segments are hung from the cable system and assembled piece by piece into a continuous bridge spanning several kilometers. This is the true holy grail of Norwegian engineering, a structure with no precedent anywhere in the world. For fjords that are both extremely deep and heavily trafficked, or where weather conditions are too harsh for floating bridges, engineers have proposed building massive concrete tunnel tubes suspended about 30 meters beneath the water's surface. These submerged tunnels are wide enough for 2 lanes of traffic, and are stabilized either by floating pontoons on the surface or by being anchored to the seabed with cables. By remaining below the surface, the tunnel avoids the destructive forces of storms and waves, while also allowing massive cargo ships to pass freely above. This is not just a transportation project. It is an engineering marvel that redefines how humans may cross oceans in the future. Although it may sound like something out of a science fiction film, the concept of a submerged floating tunnel has moved beyond theoretical designs. It is the result of decades of intensive research led by the Norwegian Public Roads Administration, in collaboration with leading experts from the Norwegian University of Science and Technology. As of 2026, massive drilling operations have already reached depths of nearly 400 meters beneath the seabed. This is no longer just a concept on paper. Millions of tons of rock are being excavated every day to create what will become the longest and deepest subsea tunnel in the world, laying a solid foundation for even more complex structures in the future. To protect this megastructure from the destructive power of the ocean, engineers must confront a silent yet relentless enemy: saltwater corrosion and the immense pressure at depths of hundreds of meters. Instead of using conventional materials, the E39 project employs ultra-high-performance concrete, UHPC, with a densely packed aggregate structure to prevent chloride ion penetration, combined with cathodic protection systems, a technique that uses low electrical currents to prevent metal corrosion, similar to technologies used on modern aircraft carriers. For the deepest subsea tunnel sections on Earth, such as Rogfast, where water pressure is extreme at depths approaching 400 meters, the tunnel lining is cast from ultra-high-strength concrete, capable of withstanding massive compressive forces, integrated with a network of fiber optic sensors to monitor structural deformation in real time. Beyond physical durability, the project is also a smart system, utilizing AI to analyze data from hydraulic dampers, allowing bridge spans to automatically adjust and reduce vibrations during powerful Arctic storms. Why is Norway willing to spend up to $50 billion just to save 10 hours of driving? The answer lies in a complete restructuring of the economy and society along its western coastline. This region is the heart of Norway's seafood and energy empire, contributing more than 50% of the country's total exports. Eliminating slow ferry crossings will unlock the logistics supply chain. Thousands of trucks carrying fresh salmon can reach European markets faster, saving hundreds of millions of dollars in operating costs each year. From a social perspective, the E39 will erase the boundaries between communities that have long been isolated like separate islands for centuries. The project will create a unified labor market where people can live in peaceful coastal villages while still commuting to major urban centers like Bergen or Stavanger in under an hour. Not only is Norway pushing the boundaries of engineering, but the world has long stood in awe of era-defining megastructures. For Americans, no structure is more iconic or proud than the Golden Gate Bridge in San Francisco. Completed in 1937, it is not just a vital transportation link, but also a symbol connecting history with the distinctive elegance of Art Deco architecture. With its striking international orange color and a main span of 1,280 meters, the Golden Gate has stood as an engineering marvel, defying dense fog and powerful Pacific currents for nearly a century. However, when this legendary icon is placed beside Norway's proposed Sulafjorden crossing, a staggering comparison emerges. America's symbol suddenly appears unexpectedly small. The difference is not just in dry numbers of scale, it represents a leap forward in materials science and marine dynamics, unlike anything the world has seen before. If the Golden Gate Bridge marks the pinnacle of traditional steel and suspension cable engineering, then Norway's project is an answer to what once seemed like science fiction: infrastructure built to conquer the open water.
Welcome to Israel, a nation often portrayed in news headlines for its conflicts and sun-scorched deserts, yet in reality home to some of the most extraordinary landscapes on Earth. From the ancient city of Jerusalem with more than 5,000 years of history, to the non-stop 24-hour coastline of Tel Aviv. From the Dead Sea, where the salt concentration is so high that your body floats effortlessly, to lush nature reserves, thriving in the heart of the Negev desert. Together, They form an Israel that feels both familiar and unexpectedly striking, a place where harshness and abundance coexist on a narrow strip of land. With a GDP per capita exceeding 54,000 USD, Israel is not just wealthy, it is surging forward on the strength of technology, energy, and maritime infrastructure. Located at the crossroads of three continents, yet surrounded by long-standing tensions with Lebanon, Syria, Palestine, and Iran, Israel understands one fundamental truth. Without expanding toward the sea, it cannot grow. So it chose a bolder path, transforming the Mediterranean into the nation's second strategic frontier. That is why more than 600 million cubic feet of seafloor were dredged to create the Haifa megaport, a massive harbor built from rock and soil lifted straight out of the ocean. Meanwhile, at depths of 3,000 meters, the nearly 2,000-kilometer East Med pipeline is preparing to redraw the energy map between Israel and Europe. And offshore, Leviathan, a colossal gas field holding more than 22 trillion cubic feet, is turning Israel from an energy-poor nation into an emerging gas powerhouse. Right now, let's take a journey across Israel and discover how this small country is transforming the Mediterranean into the launchpad for its infrastructure ambitions. And our first stop, the monumental expansion of the Haifa megaport. Did you know that to build the Haifa megaport, Israel had to dredge hundreds of millions of cubic feet of the Mediterranean seafloor, literally turning the ocean into the foundation of an entirely new mega harbor? For decades, Haifa had been Israel's busiest port, but before 2010 it was still too shallow, only 30 through 47 feet deep, making it impossible to receive the massive container ships arriving from Asia. As trade with Eastern economies surged, accounting for 25 to 30% of total imports, Israel was forced to expand this critical gateway, and that was when the Haifa megaport project was born. But why Haifa? Israel had to expand Haifa for a simple reason. It had no other choice. The entire country has only three major seaports, Haifa, Ashdod, and Eilat, and each comes with serious limitations. Eilat, though closest to Asia, is only 31 to 33 feet deep and sits next to the fragile coral reefs of the Gulf of Aqaba, making dredging or expansion nearly impossible. It also has no railway connection to Israel's economic centers, forcing goods to travel more than 280 kilometers across the Negev desert, driving logistics costs sharply higher. Ashdod, despite being modern, is constrained by a short coastline and heavy sedimentation from the south, leaving almost no room for large-scale expansion. Meanwhile, Israel's booming trade with Asia demanded a deep-water port capable of receiving 15,000 to 18,000 TEU container vessels. Haifa was the only location that could meet all those requirements. A wide offshore area suitable for land reclamation, proximity to Tel Aviv, Jerusalem, and Haifa Bay, the most developed road and rail infrastructure in Israel. And, crucially, no coral reefs that required protection. For these reasons, choosing Haifa was not a coincidence, but a strategic move that would transform the city into Israel's largest logistics hub of the 21st century. To transform Haifa from a shallow water port into a modern megaport, Israel divided the expansion into two major phases, each one marking a leap forward in the country's ability to handle large cargo ships. Carmel Terminal was the first expansion project. Construction began in 2003 and operations started in 2010. The project involved reclaiming an additional 2.4 million feet of land and dredging roughly 88 million cubic feet of material from the seabed of Haifa Bay. The channel depth was increased to 51 feet, allowing the terminal to accommodate post-Panamax vessels. On the newly reclaimed land, Israel built a quay over 3,100 feet long, installed 6 modern ship-to-shore cranes, 12 automated yard cranes, and turned Carmel Terminal into the largest transshipment hub in northern Israel at the time. But as trade with Asia continued to surge, Carmel quickly became overloaded. Israel was forced to look for a new solution, and Bayport Terminal was born. Bayport Terminal, part of the national Haifa Bayport project, began construction in 2015 and officially entered operation in 2021. This was the true quantum leap for Haifa. Israel dredged more than 520 million cubic feet of sand, silt, and hard rock, an enormous volume 6 times greater than Carmel. Of that total, 353 million cubic feet were used to create a 207-acre artificial island, forming the foundation of Bayport. The navigation channel was deepened to 56 to 57 feet, suitable for vessels of 18,000 plus TEU. Its ship-to-shore cranes, yard equipment, container yard layout, and automated gate systems all meet international standards, allowing Israel for the first time to enter the big league of Mediterranean megaports. So how did the Haifa megaport transform Israel's transport capacity and elevate the country to an entirely new level on the global trade map? Previously, Israel could only receive ships under 8,000 TEU, but with Bayport and Carmel, Haifa has raised the standard to 18,000 to 20,000 TEU, equivalent to Europe's major megaports. Its container throughput capacity surged to 1.53 million TEU per year, allowing Israel for the first time to compete directly with Mediterranean hubs such as Piraeus and Port Said. Beyond increasing capacity, the Haifa megaport also significantly reduced logistics costs. Larger vessels can carry more cargo per voyage. Handling speeds have climbed to over 190 containers per hour, and the automated systems ensure smooth operations even during peak surges in traffic. As a result, goods from Asia bound for Israel no longer need to be transshipped through neighboring ports, shortening transport time and strengthening Israel's strategic economic independence. Can you believe it? One of Israel's most strategic megaports is operated by a Chinese company? That's exactly what turned the Haifa megaport into a global flashpoint. When Shanghai International Port Group, SIPG, the operator of the world's busiest port, handling over 47 million TEU per year, won the contract to run Bayport for 25 years, they brought to Haifa the same level of automation found in mega hubs like Shanghai and Ningbo. Thanks to SIPG, everything from remote-controlled quay cranes and AI-based container recognition to high-speed traffic management systems was implemented, pushing Haifa's handling efficiency to over 190 containers per hour. But with that came a geopolitical earthquake. The United States immediately raised concerns, as Haifa sits only minutes away from the anchorage used by the U.S. Sixth Fleet. Several Israeli lawmakers questioned whether handing over the keys of such a strategic asset to China could compromise national security. Some analysts even called the deal a new flashpoint in the U.S.-China rivalry, right on Israeli soil. Despite the controversy, Israel still chose SPG, because few countries possess both the capability and the willingness to invest in transforming Haifa into the 20,000 TEU megaport it is today. If Haifa megaport was Israel's way of expanding its footprint toward the sea, then the EastMed pipeline is how the country seeks to extend its influence beneath the sea. After building a megaport capable of receiving 20,000 TEU vessels, Israel understood that maritime infrastructure alone wasn't enough. It needed a strategic energy corridor linking directly to Europe, reducing reliance on routes that pass through Turkey and the Suez Canal. This is why the EastMed pipeline was conceived, a nearly 1,900-kilometer natural gas pipeline stretching from Israel to Greece, with many sections running at depths of up to 3,000 meters, deeper than most submarine telecommunications cables. If completed, it would become the longest and deepest subsea pipeline in the world, delivering around 10 billion cubic meters of natural gas every year from fields like Leviathan and Aphrodite straight to Europe. Though not yet built, the project represents far more than an energy link. It is a bold geopolitical statement. Israel, Greece, and Cyprus are forming a new energy triangle, directly challenging Turkey's influence in the Eastern Mediterranean and reshaping the balance of power across the region. Have you ever wondered, where do those thousands-kilometer pipelines and massive offshore ports get their energy from? The answer is the Leviathan gas field, the giant natural gas reservoir lying beneath the Mediterranean Sea, and the very source the EastMed pipeline is designed to deliver to Europe. Located about 130 kilometers off Israel's coast, at a water depth of more than 1,700 meters, Leviathan holds over 22 trillion cubic feet of reserves, making it the largest gas field in the Eastern Mediterranean. Discovered in 2010 and brought online in 2019, Leviathan immediately shifted Israel's energy posture from a nation dependent on imports to one exporting gas to Jordan, Egypt, and soon reaching even the European market. The Leviathan development is also built on a scale just as unmodest as Israel's maritime megaprojects, a production platform weighing more than 30,000 tons, wells drilled over 5,000 meters below the seabed, and a network of high-pressure pipelines stretching hundreds of kilometers beneath the ocean floor. If Haifa Megaport is Israel's way of expanding its footprint on the sea surface, and the East Med pipeline is its plan to control flows beneath the sea, then Leviathan is the energy heart powering that entire ambition, a piece without which no project could function. Israel, once a small and constrained nation, has chosen a completely different path, expanding toward the sea, mastering the seabed, and harnessing power from beneath the ocean floor. Haifa Megaport gives them a new commercial gateway. East Med Pipeline opens a corridor linking their energy to Europe. And the Leviathan gas field transforms Israel from a gas-poor country into a rising force on the global energy map. These projects are not just constructions, they are declarations that Israel will shape its own future, no matter how harsh its geography may be. Thank you for joining Terran Works on this journey into Israel's maritime ambitions. If you want to keep exploring the megaprojects, quietly reshaping our world, don't forget to like, share, and subscribe. See you again in our next stories.